Thanks. Recording 되고 있는 거 봐요. Pause. Yeah, good. Okay. Let's do it. Hello. So here we are. There was can you close the door? Okay. Okay, so thanks for coming. And for being flexible. Thanks a lot. So it has been a lot of fun. So let's finish this QFT discussion that we've been going through throughout the semester by now actually discussing how we should actually think about the S metrics in a more, if you like, non-perturbative sense. Okay? How can we define a S matrix in a non-perturbative sense? So that's the goal, and ultimately we want to talk about Green's function or endpoint correlation function of Heisenberg picture operators, and then from that we want to derive what is known as the reduction formula. I think it's okay, probably. I mean, so long as you guys can see the board. But I think we didn't finish the discussion that I sort of gave you. Okay, if I want to compute the two-point function, so if you wanted to compute the two-point function in the sense of a perturbation theory, then first we talked about, okay, I want to compute this, and then I will start adding some block where this can include a lot of perturbative corrections that you can imagine, right? So for instance, in a theory that we talked about, you may include that, or you can also include higher order corrections and so on and so forth. And then with this block, you can imagine of having sort of a geometric series structure like that. And I told you already that naively adding or correcting two-point function in this sense breaks down because there is a parametric suppression from the fact that this comes from the higher order in perturbation theory, but also there is a kinematic enhancement because it has extra leading mode propagator, which has 1 over p squared minus m squared. Okay, so that I told you that if I call whatever this factor, like this factor I call minus I sigma, you can do at g over at g squared, or you can also correct up to g to the fourth, whatever. But whatever that is, if I call that to be minus I sigma, I told you that the right thing to do is a result entire series. And then if you do that, you get p squared minus m squared minus I sigma. Sorry, just if you do it correctly, which I think I did it at least this much. Okay, so far so good. Now, if you just compute this, good luck, first of all, but say you manage to compute it, but then first of all, you're not going to get the sensible answer, and how to compute this object, how to think about those objects will be the subject of QFT2, okay? So it's the theory of renormalization. But for now, let's pretend we know what that is, okay? So pretend we have done the job. We computed it, and this is dimension 2 object because it sits together with the p squared and f squared, right? So it is a dimension 2 object, which is a function of a p squared. So by power counting, meaning by just looking at the dimension of that, can you how far can you see, student? Like if I write this, can you see? Okay. No. Yes. Good. Okay. So something around. Oh, that's why probably there's mark all the way here. Okay. So if you do it, then you can expect that this function, this is as a function of external momentum p squared, takes the following structure, something like a, something that we don't know, times p squared. This is dimensionless quantity, and then something that doesn't have any p squared dependence, and something which is leftovers. So let me explain this structure real quick, and then we are going to use that. So A, this is dimension 2 object. So the fact that first of all B doesn't have dimension 2 means that naively it is proportional to what is known as UV cutoff scale. Okay, so if you naively compute it and letting the loop momenta can go from 0 to all the way to the largest possible momenta that theory can admit, because I demand that this doesn't have a momentum dependence, the only dimensional quantity of this thing can possibly be is lambda squared. Now, this has explicit p dependence, but in principle, it can have some logarithmic dependence to the UV cutoff. But okay, you don't worry too much about what I'm talking about here. Okay, don't worry too much about if this sort of thing doesn't make sense. Okay, this is supposed to be a subject of renormalization. But I just wanted to tell you that in principle, this complicated looking object always takes this possible form, regardless of computation, whatever computation you do. Okay, this is a generic statement. And there are pieces, which is a polynomial function of a momentum, external momentum. And there are pieces which in principle is not polynomial function of the external momentum. So okay, now I'm going to the boundary of that. Oh shit. Okay. So let me say in word. So I want to say two things. This is an elliptic in p squared because it's a polynomial function. And then if you Fourier trace back to the position space, an ellipticity momentum means the locality in position space. Okay, so they correspond to something captured by local physics in position space. This is a disk statement, so nevertheless it's true. Okay, however, so that's the first thing. Okay, an analytic function of the momenta, therefore it's a local in position space. That's point number one. Point number two, but they in principle and in general they do have a UV sensitivity. High. Okay. So they in general has a sensitivity to the UV cutoff scale. Okay, so that's the first piece. And this thing will have opposite a complementary feature. This generally is not analytic in momenta, external momenta. Okay, so therefore, this is in general no local function of a space and time. But this will be UV insensitive in the sense that this doesn't have any dependence on, say, UV cutoff scale. Okay, now I said a lot of words that doesn't make any sense to you. That's okay. Okay, so just understand what I just said in like 2 minutes is the subject of like 4 lectures. So good. Okay, don't worry too much about it. But just by that, you can this takes this form. Okay, at the moment it's totally okay that however you compute this, it will always take this sort of form. That's all that is necessary for you. Okay. One thing that you certainly know is that A, B, and the sigma tilde are all, say, order G squared if you have done the calculation at G squared, right? That you can see. This is all G squared. How do you know that? If you take G squared equals to 0, they should go away, right? So each of those pieces must have that dependence. Okay, universal. At least you see. Can you buy that? Huh? So what I just said is this. Suppose let's compute sigma at G squared order, meaning just compute this little one single loop. Then everything contained in this calculation is order G squared. Now I just divided, separated, decomposed the sigma into 3 different pieces. But nevertheless, all those pieces will be order G squared. You can argue what if I subtract +1 - 1 modulo that. Okay, that is nothing but known as a renormalization scheme. But again, that's another topic. So why am I saying this without even telling you anything about renormalization? Okay, because it can tell us something about unitary already. So that's the thing that I want to go into. So now let me write down propagator according to the form that I suggested. So let me just use that. Okay, I have 1 minus a b squared m squared b sigma theta. And then here I'm assuming that a, b, and sigma theta are all order g squared, meaning they are small. So I have done all the yes.
I understand the sigma theta is lambda.
Your question is, how do you understand that?
I mean, so maybe lambda theta, no, sigma theta is not uniquely defined in the definition of polynomial and not polynomial part.
So what is it unique is that that's true, but that's true, and that is fixed by, again, what is known as a renormalization scheme. So you can shuffle around some finite case from B to here, and so on and so forth. Okay.
So I understand that sigma theta is independent of lambda.
You can understand that.
Okay.
Yeah. Okay. If that is good enough answer to you, yes, you can understand that. And there's a very generic technique that allows you to understand why sigma tilde must be UV independent. But again, that's a subject of QFT2. Okay. So let's continue from here. So again, I'm assuming A, B, and sigma tilde are small corrections to whatever, like 1, n squared, and 8. Okay, the pair leading mode propagator, which means that I can treat A, B are sort of small numbers. So that means that I can write this as I. So basically, I'm gonna take this out of it. Let me first do that. So 1 minus a, I can take that out of it. So b squared, then m squared b divided by 1 minus a, and then sigma tilde minus, right? Of course, I put that out of it. And then I'm just gonna view 1 over that thing as I of z, some number, which I'm gonna write immediately, and then b squared, and then let me expand this object also, because I'm treating a as a small number, and also I can expand this too, because again I'm treating a as a small number, and then where I define z to be 1 over 1 minus a, which is roughly just 1 plus. Okay. So then, okay, whatever. There's this complicated object, but it looks like p squared minus some mass looking object, right? And then some horrendous function of momentum. Okay. So already at this point, you start seeing 2 things. One, well, it is not 1 here sitting, but there's some numbering principle once you start including higher order corrections in perturbation theory, right? But if you want to have a fully, completely, solve the theory, you want to see eventually that, ultimate propagator 2-point function looks like I over p squared minus actual mass squared, like measured physical mass squared. Okay, that's what you want to see with number 1, because that corresponds to, say, unit probability of having propagator. Now there's some weird factor up here, which is not even integer, because this can be 16 pi squared, g squared, blah blah, all of that. So this factor is not, first of all, z appearing in this form is known as well, a bad name, but I think it's good to know the bad name too, because otherwise you would know what other people talk about, right? When other people speak bad things. So wave function renormalization factor. Or Coleman suggests that this is historical accident, because people were confused between quantum field versus wave function. We talked about that, right? So what? Field, sometimes called strength, basket, renormalization. So for instance, you can ask, how can I make 2-point function that looks like basically just I over something rather than IZ over something? Well, you can do it by saying, oh, divided by that stuff. So z minus half pi vacuum. Z minus half pi vacuum. Then we look like this I over t squared minus something that I will come to this version, right? So if I just divide by one of that, both sides. That means if you call this to be now your actual U field, meaning now this is to be normalized field, then two-point function of a renormalized field will have a propagator that start up 1 times I over p squared minus something. Okay? So that's first thing that we can learn from this without knowing how to compute this thing at all, without knowing anything about renormalization. Right? We can see that. Second fact. Now, I told you that this sigma tilde function is, first of all, not analytic in general. For instance, this can contain something like log of p squared minus whatever, some m squared, stuff like that. Okay, so this is not analytic. How do you see that? Because this is a multi-valued function. How do you see that? Well, just to do 2 pi rotation, if this is a single valued function, as you go around the log, it should go back to itself. But because of the log, it shifted by 2 pi I. So, for instance, if this thing had p squared over, I don't know, m squared, then under this, it picks out about 2 pi I plus log p squared over m squared, things like this, right? So it is multi-valued function. So it is non-analytic. So whenever you have a multi-valued point, it's called the branching point. Whenever you have a branching point, there's going to be a branching cut coming out of there. And another thing you immediately notice is that because of this feature, oh, there's a imaginary part popped out of it, right? So because of this generic property, okay, which takes the time to actually learn all these properties. This function that I split into this way generically include imaginary components. Why am I talking about imaginary component now? Recall, unitary says that minus I times some amplitude. Okay, imaginary part of the amplitude is related to this nice looking sum, and then what was that? I'm not gonna tell you. Right? So now let's ask or apply this unitarity equation to just one-to-one, 2-point, meaning propagator. You can ask, oh, how do I ever get the imaginary part of the propagator? Okay, the source of the image, so up to this side, this is not counted as the imaginary part, okay? So imaginary part, if you look at the denominator, that's the right way of looking at it. This is real, this is real. And imaginary part should talk the sigma tilde, and I'll just try to roughly explain to you, without telling you how to compute the thing at all, that this generically includes imaginary part. Okay, that is captured by this. So now let's just use this formula to actually determine the imaginary part of the propagator without never knowing how to compute it. Okay, so again, let me say that again. The proposal is let's use unitary equation to determine the imaginary part of the 2-point function. Okay, this will allow us to write down a nice form of 2-point function without learning about loop calculations. Okay, so we're already there, right? So minus I times, well, that's 2I imaginary part of the 2-point function. Let me just write it as sigma. Okay, so I'm just writing sigma like this, and that is equal to, you know, final. This is what? This is literally like product of the final state particles and then Lorentz invariant measure. We talked about that. And then there is decay amplitude, right? This is amplitude from the one particle because I'm looking at the one-to-one to multi-particle. So this is describing one-to-many particles the process, and then there's momentum conserving delta. So what is that? This is nothing but 2 times energy of the decaying particle, initial particle, and then decay rate. Right? That describes 1 to n, where obviously this is total decay rate because this is somewhat entire decay chance. So what we learned, therefore, is that in major part of the sigma that you should be able to compute it at some point is nothing but canceling out the factors of 2, going to the center of momentum frame, decaying mass of the decaying particle times total decay rate. Right? This is what the unitary tells you, even though you haven't computed the sigma at all. Right? So then, with that much of information, then what one can say is that eventually, this propagator with all the loop corrections will take the form that I times d p squared minus actual physical mass squared plus I m gamma. After all dot subtle, eventually it will take this form because I just determined this measuring factor from the unitary constraint. Okay, so that's, for instance, how powerful this theory can be. Okay, so this will be the end of the discussion about the unitary, and then I will move on to Green's function and the LZ. But before that, are there any questions? Okay, this is a subtle discussion again, and that it needed a little bit of input from the renormalization sort of story, but there are parts that obviously I'm not expecting you to understand. Those parts, don't worry about it. But the only input that I needed to use is that somehow all the loop corrections can be factorized into this form, and then the fact that in general you expect that this can have imaginary part. Only with that much of a knowledge, you can ask yourself, oh, can I determine the form of the imaginary part? Just from the unitary equation, and the unitary told you that imaginary part got to be mass times decay rates. And then I just put it. This is very close to probably any confusion exists. If I go to the pole position, it would look like this. Not everywhere, but close to the pole position. Superposition will look like this. That's it.
대신 피지컬한 函수가 실험하는 사람들이 특정하게 될 때.
That's right. So yeah, so you see, so this is just number, but this is a function of momentum, right? So and then I told you that this doesn't look beautiful at all. This will be ugly looking object. But then here I'm just writing a piece for only. What happened? This is a complicated function of momentum. I first figured out the pole of this function, like genuine pole of this function, and then I went into the pole in the complex plane of the momenta, and in the vicinity of the actual pole of this propagator, which is what experimentalists will measure, this will look like this. That's what I meant. Okay, so a lot of lines, but okay, these details will come in eventually when we study normalization. Any other questions? Yes.
Why don't you consider
Here what? You mean sorry? Are you saying in the G coupling constant expansion or something else? You said pure what? Pure fourth term. A speed to the fourth term. You mean not this, but the speed to the fourth? I consider that as still a analytic part. So the claim is that the sigma, not sigma tilde, can always be written as some number times p squared, just number, and then the rest, which will be so entire analytic piece will be only this, nothing else. And this includes only non-analytic piece.
could you explain about why
Only this factorization happens. Okay, so I didn't explain actually at all. I claimed it. So am I well, it's okay. So in order to see that, okay, you have to write down actual one node integration, actual expression for this, and then one can divide by this, and then one can do. You can keep dividing by this. At some point, one can show in general on a general ground, but in order to actually see that, you actually have to write down this expression, this thing. Okay, then this is always like UV insensitive, like meaning now this is finite. By finite, I mean now it only has the 1 over lambda power dependence, and then you can integrate backward. And these are integration constant, and you integrate backward. So anyway, it needs a little bit of step to explain, but it's doable. I have this for offline. Okay, any other question? Yes. Yes, you.
The final.
Not you.
I call it the people with and difficult.
You're talking about here now?
Okay, I'll put up for you. That's exactly.
Oh, you mean these two?
Yeah.
It is entirely true, not exactly.
Is there any physical observable consequence of not being in fact?
Yeah, there are. So when I say this, so when I say that in the complex plane of a momenta, right, this is Pareto's function of momenta, and then there's actual physical pole. Actually, it might be here. Okay, there's actual physical pole. And then there can be some crazy analytic, like crazy cuts here, whatever. There, something like that. Okay, so I'm saying I zoomed in there, and then only around in the vicinity here, it looks like that. Your question is there physical implications? The fact that the full propagator is not actually just of that, but there's something else. In principle, yes, because if you try to produce a particle, that particle by some collision of other particles, but if you choose S, the center of mass energy, in such a way that that is not actually equal to this, then the produced particle is highly off shell, not on shell. So you're not actually going to the on shell region, but you might be exploring some other regions here. But satisfying this, we talked about this Mandelstam Kibble plane, right? You have to satisfy, you should be here and there and there. So if you manage to create such region, but in such a way that collision of this particle doesn't really produce this particle on shell but highly off shell, then in principle you can explore other regions and other analytic property of this propagator. Okay, in principle. In practice, we are very much interested in going to that because we want to discover that particle. And best shot is you go to the on shell, and this is a maximized. You have a high cross section. You have a best chance to actually discover that particle. Yes, you had a question.
이 시기에서 PI가 어디로 왔고 그리고 M이
Yes.
파티클 한 개가 M개로 지키는 과정에서 파티클 넘버 M인지 아니면 SM인지.
Oh, sorry. Yeah. Okay. So location. First of all, two canceled, and then I minus I collide to be 1. So that's why this didn't appear. That didn't appear. So I just wrote down this. So my notation is N used for many things, but here N denotes on a general ground intermediate state. It can have a 2 particle, 3 particle, and particle. So my notation is that decay rate, decay width for this particle to decay to a state characterized by this letter M. Okay, and then I have the sum of all possible final state channels. Did I answer your question fully or still? Oh, this is a mass now. Oops. This is not mass. This is total decay width. By total decay width, I mean it's the entire thing. I'm just calling a total decay width. And then I just went into center of the momentum frame to change M to the mass. Okay. Good. Any other question? Yes.
And physics scale is what we find from what it looks like it is dependent on B, and the B is dependent on the UV.
Yes, in principle, it is okay. So in a sense that there's a UV sensitivity, and secretly the mass parameter you had in your Lagrangian also has UV sensitivity. And they play that in such a way that this overall, I mean, not just this, but if you zoom into the whole region, there's also contribution from this piece. Everything just, this is conspiracy theory. So they all of a sudden conspire to be totally UV insensitive, and that is observed mass. Okay. So again, this requires at least 1 month or maybe 2 months of lecture to fully explain all this interesting and deep subtlety. Any other question?
시그마 필다의 리얼 부분은 지금 피지컬 베스에 들어.
Sorry, say it again.
그러니까 피지컬 베스에 일단 시그마의 리얼 부분이 포함되어 있는 거죠.
Sigma, say it again. This includes what?
피지컬 베스예요.
Yes,
거기에 이제 시그마 필드의 리얼 부분도 포함되어 있는 거죠.
that's right. That's correct. So exactly. So if I write down this, and then let me say every this thing to be just m squared r for reasons. Sometimes we normalize mass, but then sigma tilde has a real part of sigma tilde, and then imaginary part of the sigma tilde. I already told you how to determine this here. So now let's go to the region where this becomes 0. Okay, this is a function of momentum. So I choose a momentum such that this becomes 0. Okay, so then I call that value to be my m physical. Good. Okay. Again, yeah, good that you guys all extract all those informations, but you're not supposed to. Okay. So this again, this is the whole separate lectures. Any other question? Good. Let's move on. What happens if I click? Would it be wet for a while, or I can use it right away? Okay, but that means I shouldn't or should I can. You could. Okay. Next time. By next time I mean maybe I write a lot of things and then I have something to explain in Word and then I can do it while I'm explaining. Okay, so that's all about the unitarity that I wanted to talk about. And the reason why I wanted to go into this discussion is A, it introduces you the notion of wave function renormalization automatically, okay, which will occur in a minute, which maybe talk about reason. Okay. So the last topic of the discussion so I'm gonna cut through the short path to get to the point. Okay, but you may want to read the Coleman carefully because there's a lot of germs in the discussion. And you may have noticed that I never introduced this little f of t function, where Coleman really used it heavily, like this turning on and off function. If you have things, how to understand a static state and so on, but I never introduced that. So I had a hard time because now in this part of the discussion, he's heavily trying to understand with f, without f, how to go from one to the other, but I never introduced it. Nevertheless, I have to explain this without ever talking about f of t, right? So here is how I managed to figure it out. So let's recall the following facts. So given Hamiltonian or Hamiltonian density, right? What we talked about was that if I can split it into two pieces, I don't know how, but some pieces that I understand very well, some pieces that I don't, for instance, right, interaction part. Then what we said is that if there is a operator, say in the Heisenberg picture, first of all, let's first very quickly review, and there is a Schrödinger picture, then the operator in Heisenberg picture rotates according to the full time evolution operator. First of all, right? And then operator in the interaction picture rotates or time evolves only according to this H0 piece, right? And then in this picture, then we talked about the fact that the state, on the other hand, in interaction picture evolves according to the rest of it. And then this time evolution operator that that you need to understand the time evolution of the state is basically full time evolution, but canceling out the part that is used already for the evolution of the operator, right? So that we already talked about. This is your summary. Then what we learned is that it turns out this time evolution operator, this thing, like T prime, is nothing but given by Dyson formula, like T prime T. Let me just write this way. H. Where this is interaction Hamiltonian in interaction picture. So we talked about that. Good. Now, what I want to study is the following. So what I want to study is the following. So consider a Hamiltonian, the Lagrangian, for the same matter. Okay. So that thing has, again, H is 0 and the interaction that I'm interested in. Okay. So for instance, this can be G, phi, that we've been studying so long. But I want to also include a term that that looks like phi of x, j of x. So okay, just to clarify, in Coleman he's gonna use rho x, but I use the j of x because this is like universal notation in this field. So this j is called a source. I will explain in a minute why it is called a source. So so these two were original H. So in order to make a distinction, so let me keep this H just without anything for this term, original one, and then let me just put what do I put? Tilde, same there, to make a distinction. So H tilde is H supplemented with a source term. Okay. Now let's first explain what this source term does for you. So imagine there is a supported space and time where this is a region of space time where J is non-zero. Then what it does is that this can actually shoot out this phi particle. Okay. So in that sense, this is the source. This can create a particle. And we are totally agnostic about like how this looks like, where they come from, and so on and so forth. If you like, this is a mathematical machinery, as you will see soon momentarily, extremely useful machinery. But if you want, this may be made of secretly, nuclear anti-nuclear annihilation to actually produce the phi. But somehow I created a machine in the lab that there are these two sources inside of that. If I turn that on, somehow if this thing happens, it actually produces phi. Okay? So there can be some actual microscopic theory, like how this J source thing works out, but I'm not interested in. I just want some God for this particle phi. That's all that is for now. Okay? But people at the LHC are super interested in how this thing works. Like they have to create a beam, very good, high quality, no high quality and very high energy stuff like that. No radiation, blah blah blah. they're super interested in designing how this works. But for me, I'm just writing this table. Okay, that's my source. Now, I'm gonna do the following thing. So I want to ask the following output. Let me first write in Word. Oops. Can I write vacuum? How do I write? 2U, right? Help me. This is second last lecture. I'm fading away. So vacuum to vacuum transition amplitude. It's a long name. In the presence of source J. So I want to look at the object, mathematical object, which I will write momentarily. I want to go from the vacuum. So suppose I take this is my time. This is my time. I want to go from the vacuum, meaning I don't want to see any particle there. And then end with the vacuum. Again, I don't want to see any particle there. But I want to have a source. So diagram will be something like this. So this block is where J is supported. Okay? So under J, then they can create the particle. Something can happen. Whatever. J. So as a promise, in the very far past, nothing was there. Okay, so there was no particles in particles. So I start out with the vacuum, and then for future, again I went back to the vacuum. Okay, so schematically, let me write it. So what's the point here? If I supplement my theory with this source term, then I can ask vacuum to vacuum transition amplitude, and then there's a lot of diagrams that pop out of this, right? Something that looks like this. And you haven't seen diagram that looks like this, right? And the only difference was that before you didn't have a source and you interpret this as a scattering process, right? You ask them, okay, 3 particle comes in, colliding happen, 4 different particle comes out. So here, it's just that the source was attached to the end of the line, and in principle, these line can be off-shell because this is part of internal lines. But to the extent that if I'm pulling this very far from the interacting point statically, they want to be more and more on-shell. Why is that? Basically, why, if I bring this further away from the interacting point, why do they want to be more and more on-shell? Sorry. That is because you're asking long propagation. You can ask yourself, when can you have a high probability for long propagation? And 2-point function is maximized when the denominator goes to 0, right? And then when the denominator goes 0, you call that an on-shell, correct? So when you pull these lines further away from the interacting point, this becomes on-shell. So this is how we are going to play with this source games, okay? Source terms. All right, so that's the setup. Now I want to study. So you're going to remember this. You're going to know this. Yes? Okay? Heisenberg picture, interaction picture, and then they are related by this relation. Okay, I'm going to write one more thing. Not now. Okay, let me first set it up. Anyway, I think I have to write it again. Okay, so what I want to do is the following. So again, I want to study vacuum to vacuum transition amplitude in the presence of source. And you see that from this picture, this is capable of capturing the entire scattering amplitude of the theory. Right? Again, let me say that again. I'm just gonna look at a single object, which is basically vacuum to vacuum transition. Looks like, oh, you're just looking at a single object. But my claim is that if you turn on the source, that single object includes the entire dynamic information like that. Okay, so let me write that statement in the equation now. So I want to define, so in other words, now there's H tilde. I told you that there's H plus phi of J. Okay, there's the source term. Now I'm going to treat this as if my H0 term, meaning the thing that I understand very well. And then I'm just going to treat this as my, say, interaction term. So, okay? So in this division, in this decomposition, then what I call like what I call, interacting operator is actually, full Hamiltonian picture operator. We call this originally was transforming only according to H0 transformation compared to the shredding picture, right? But now in this division, H0 is nothing but the entire original Hamiltonian. So this is a full evolution by full Hamiltonian. So in this division, then what I used to call interaction picture thing is nothing but full Hamiltonian operator, picture operator. Is that clear? Good. Then, again, in this division, then what I used to write as a U of P prime is nothing but time order expansion, time order exponential of d for x, and then phi of x, j of x. But now, once again, this is Heisenberg picture operator. Okay, so originally you had h of I in interaction picture Hamiltonian. But now interaction picture, so this is first of all interaction picture Hamiltonian, but in that picture, interaction picture is nothing but a Heisenberg picture. This is important. So let's sort it out. Do you get my point? Okay. Now let's write down the equation that actually describes vacuum to vacuum transition. So how do you do that? We already talked about that thing. So I want to go from vacuum to vacuum, but I'm computing with S matrix. So in this case, S matrix is just phi of H, J. If you're totally lost, let me remind you, there's a finite initial state with in state, outgoing asymptotic state, and then we said, okay, I can write it as three version of that with S matrix, three version of initial state, and S matrix was nothing but UI minus infinity, right? Or whatever it is, like that. And this is nothing but time order e to the minus I minus infinity. It reacts interaction Hamiltonian interaction picture. But I told you that I'm just gonna divide it that way. So therefore, the only thing that appears here is just that thing, but in interaction picture. But in the interaction picture is evolved according to this full Hamiltonian, so that's nothing but Heisenberg picture. Okay, so that's what I wrote here. That now vacuum to vacuum transition amplitude, according to this definition, is this expression. Is that clear? Okay. Now I'm gonna make a change of notation. So we so far used to say that this is the vacuum of a free theorem without any interaction, which means that really H0 acting on this to be 0. Now my base Hamiltonian included not only free part but also actual interaction in it. Okay, so I want to introduce a notation that omega is now vacuum of interacting QFT. In such a way that now this thing that not only included H0 but also non-trivial interaction has a zero energy. Okay, so my omega is interacting vacuum. this is like totally free vector. What is the relationship? So suppose I start with like free theory. There's a vacuum, there's a single particle, one particle, two particles, and so on. Suppose I slowly turning on the interaction. Then there's a smooth adiabatic process, right? Coming from the free vacuum to the interacting vacuum. There's a non-trivial process, non-trivial changes to that. So this will certainly has non-trivial overlap with that. But it can also have overlap with the other particle state in principle, as we talked about. As we will talk about. Okay, so anyway, my notation is from now on, this omega is my like vacuum of interacting field here. So therefore, here I'm going to make a change in my notation. Then I'm going to ask a question of this question. So I'm just saying the following. I don't know why for now. I'm just going to have this distinction, this decomposition. I want to study vacuum to vacuum transition in that picture. And then I'm going to call that object to be J of, Z of J. And in particular, I want to normalize, so I'm going to put norm of this interacting vacuum for now. Why? Since I don't know whether this is going to be 1 or some other number. So I'm just going to be safe by dividing by that. Okay? So that's my definition for now. So I'm going to study vacuum to vacuum transition in the presence of the source with that normalization. Any question? Yes.
So you can consider the passive integral?
So good. So certainly this will appear in the path integral, but we can also talk about it without introducing path integral. Yes. Good. All right. Let's study it.
So omega in the general formula G
Yes.
is the vacuum of H or A tilde.
H. Without a source though. Good. So that's good. This is the definition. This is the vacuum with respect to this H. Oh, sorry. Yes. No. Good. Okay. Because this one has G. Yeah. Yes. Thanks. Any other? Yes.
G is the front of S vector.
It's different from S vectors. Yes.
Why we are defining that?
Why am I defining the subject? Yeah. Okay. That's the rest of my lecture. Yes. Any other question? So I will tell you how to extract the S matrix out of the subject, and so on and so forth. Another question? Okay. Good. So I anticipate to use this right away almost. So let me erase this bottom part instead. That's okay. So I want to study this object. Now, I will show a couple of different representations of the same mathematical object. Okay, so the first representation is, so now let's pretend I'm just gonna expand this object. There's a power series in powers of J, meaning I just gonna expand this exponential. Okay, so that means there's gonna be like expansion in n, and then minus I to the n because of that, and factorial. And then there's gonna be vacuum expectation by time order H. Oops, I dropped the integration. Oh, huge integration. So let's do it. Because there's integral. Okay, so do you buy that I can expand this to this expression? Yes.
I mean, why don't you do the inside from?
Okay, why am I taking this out of that? This is a classical function. So it's not an operator, but it's a classical function, so I can just take it out. Good. So now, in the first representation of this vacuum to vacuum transition amplitude, it has so first of all, it's a power series in powers of J, right? And then the coefficient of J to the N expansion is endpoint correlation function. So it is a vacuum expectation value of time ordered correlation function of N Heidelberg picture operator. I just literally read the equation. Okay? So if somebody hands you this function, somehow God gave you that function, then if you just look at the tail expansion of that function, look at the nth power in J, and then the coefficient is nothing but vacuum expectation value of time ordered correlation function of endpoint function, which is in Heidelberg. Okay? That's representation number one. And then I can also just write, oh, I dropped the one important fact. Sorry. I just leave this one right? And then the second representation, I'm gonna say everything the same, basically, and then I'll just give it a name that this I can call G of N X1 Xn. And then the same thing, J. Let me just write it. Okay, J1 to the Jn. Okay, J1 literally means J with the X. So the second representation is instead of you having, say, a picture of an endpoint correlation function, you have this what is known as Green's function. You might say, okay, what is literally different from this one? Because I literally called this to be G of N, right? Which I did. But historically, people thought that if you have this sort of representation of some theory, okay, some object, then what you do is the following, exactly following. So you input the system. So suppose you have a system, and then you have some way of creating a perturbation to the system. Okay. So for instance, erase this part, vacuum, enter the vacuum, peacefully, nothing happened in the middle. Okay. Now you poke the system a little bit. Okay. You perturb the system a little bit, and exactly this J is the machinery that allow you to do this experiment of perturbing the system a little bit. And then you would say, okay, what is the response of the theory to you because of that experiment you just did? So J is a machinery for you to do perturbing the system, and then Green's function tells you the response of the system. Okay, so in a linear response theory, how do you do that? So if you give you some input, and then there's a response, and then you get output. Right? So you do something happens, and then you get output. You call that to be response of the system. Right? You can write down Ohm's law in this way, and so on and so forth. So in a linear response theory, you have a single power of a source, and then you read off the output, and then the proportionality factor is your Green's function. Okay? Here we are doing fully general construction where we can in principle talk about non-linear input reading off the response of the system. There? And then there's a clear relationship between that notion of response of the system to now what? Endpoint correlation function in Heidelberg. Okay, that's the second representation. And then, okay. And then I want to talk about the third representation. That will be very important to us. So that is, so this I haven't shown. So this hopefully clear where to come from. We literally extended it. This I have to show. Use some space, but I want to write here. So let me erase the name. So in third representation, what you get is, let me first write and explain. No, actually, I don't want to write it, this power series, because that. No, actually, sorry. I'm gonna fix that equation just in a minute. Then I'm gonna fix this equation. Everything keeps the same. I'm just literally replacing that portion with the following expression. Okay, so that's the expression. Let me explain the meaning of it. That thing. Oh, therefore I have to put the source of two. Playing is that thing is same as this. It takes time to write it down, so let me take a pause. And integral, thanks. It was there, but I erased it. Okay. So let me explain the meaning of these equations. What this says is the following. So far, I insist on studying that for some reason. There was a question, why are you studying that? Right? I insist on studying that. And then I show, okay, there can be two nice ways of representing that object back to the vacuum tradition amplitude, the presence of source. Okay, and wait for relation function principle. But then we completely lost the context of what we've been doing so far throughout the semester, right? So we had a nice construction of interaction picture Hamiltonian, interaction picture unitarity operator, S matrix, Feynman diagram, Feynman rules, all of that, so in that. But up to this point, like, okay, all of a sudden we started a completely new subject. But then this last third presentation of the same object back to contact to that. So this is the more familiar. Let's look at this object. Now this is in terms of free vacuum, not interacting vacuum, first of all. That's one important difference. This is in Heidelberg picture, which we never talked about so far. This is in the interaction picture operator, which we've been talking about so far. Okay, now this has the piece that we've been using so far, including the extra new pieces. So this is like sort of conventional way of we've been doing asymmetric theory, right? Scattering amplitude story. The only novel difference compared to what you've been seeing is we have this divided by this object. So far we've been more or less studying only that pieces. Okay, so we have like insertion of endpoint n number of operators, which you can imagine that it creates some sort of initial state, some of final state. So there's an initial state, final state, connected by this S matrix. And then we've been talking about how to construct the Feynman diagrams, how to compute that, what is the basic meaning of all of that. Okay, so this is the business that we've been running so far. This is the new object. I'm saying this is connected to that. Okay, so let's see. So I'm gonna show this relationship. I think it's very important, so I'm not actually prove it. Okay, but then we can ask after that, what's the question? What is the point? The single vacuum-to-vacuum transition amplitude now secretly actually include all sorts of S matrices in it. Okay, once we understand this connection. Because this is nothing but S matrix object, S matrix scattering amplitude, right? In the insertion of endpoint operators. Do you see that? Why? Because this is sort of the usual S operator. And then we talked about like I going to the F. But now you might say, I'm looking at the vacuum to vacuum transition operator. But now I actually have endpoint insertions, right? And then you know that if you have some insertions of operator action on the vacuum, it can create some sort of P1, P2 sort of state. So by wisely using these insertions, you can actually create some initial and some final state, including this S operator. So this includes entire possible SAR of all possible initial final state with S operator. But it does have a source term in addition. Okay? So this object, therefore, as I draw here, yes, you're going from the vacuum to vacuum, but in the presence of source, in fact, you are able to produce all sorts of processes like that with sources attached to it. Okay, I haven't quite established how to extract S matrix yet, but I'm just telling you that this has a structure and ingredient in such a way that it has a high probability chance to actually include in the scattering processes. That's all I'm saying. Okay, I'm not saying mathematically yet that you should be able to see the S matrix. No, not yet, because I haven't done LSD reduction. Okay, so let's make a disconnection with that motivation. Question.
여기 안에 들어가 있는 HR가 저기에서는 타임 J로 정리되어 있는데 저거하고 똑같은 HR이에요.
This one.
저기 위에서.
Oh, I'm sorry. Okay, so that's why I put it in the quote. So that HI is actually sorry. Thanks for asking that question. So this HI is actually interaction picture to this. Maybe that's actually right because this is HI, the usual kind that we've been talking so far. The actual interaction Hamiltonian rotated by H. Another question. As Coleman said, there are two kind of lectures. I like that phrase, right? One kind is totally straightforward, totally clear. There's no room for confusion. Explicit computation, but very boring. There's a lot of computation. Minus I2, I squared, blah blah. Okay, but you should be able to understand every single line. This is explicit computation. There's another sort of type of lecture which is very exciting, conceptually big, very novel. Wow, new concept, but nothing makes sense. It's all like in the air. This is exactly that thing. Okay, this is exactly that thing. So maybe you can get some deep insight out of it, but it can be abstract. It is abstract, right? Because I haven't specified any of this. Okay, but nevertheless, you have to see it, you have to learn it, you have to think it, you have to trouble with it. Okay, and eventually you have to think together. Okay, let me prove that relationship. How do I start? Let me start from here. It's going to be dirty long calculation. So be ready. Hopefully, I don't want to take too much time. Yes.
relation between the two yellow boxes or a little bit. Can I go zero?
Oh, is that right? I didn't know. Okay, you're saying there might be a name for this. Okay, maybe. I never heard of that. Okay, maybe that's true. I don't know who first proved that here. The relationship. Whoever proved that first for the first time, probably there's something with theorem with that. If there's gamma or someone else. Who said? Can you
Gellman and Low.
Low? L-O-W, low? Oh, okay, I see. Probably, but I can't confirm. I don't know. Okay, so let's do it. So I will start from here and then go there. Let's erase everything. Okay, so let's start from here. Time order. Oh, I can correct because I erased it. So here, time order expression. So here, you're not supposed to have this second term. That was my, because you see, because I wrote it in expansion in J already. Okay, so, okay, so let me correct it. Do you mind if I write like one like that? Are you be upset totally? Are you okay? Like that? Are we good? Okay. Cool. Very good. So I'm saying in the previous one, you shouldn't have a source term there because I already expanded it to write it. So if you remember, I was like trying to write down complex expression and I decided to write long expression, right? So complex expression without that thing with the J source term, but you can expand it out in powers of J, just like what we did for Heisenberg picture 2, and then divided by okay, so obviously when I write down d for x, I mean, there's a temporal component, time component, and I'm saying there's two time limit. I'm sending a limit to the positive infinity and negative infinity. So let's work it out. So because of time ordering, this is nothing but remember, so this is nothing but ui of t in this example, t minus t plus, right? So that is the time evolution operator in interaction system. So now I can write. So also let me just assume that I have written these operators in order of time now. Okay, this is earliest, this is the latest. Now I'm not losing any generality here. If you give me a set of n operator, and if you tell me the time of each of them, I can always rewrite in such a way that it looks it is in the order of time, right? Because there's a time ordering operation sitting there. I can just write the way and just write the name according to 1, 2, 3, 4 to the n. Okay, so that's what I have done. Once again, this is in order in time, n to 1. Good. So then let's go. First step, and then I can write as follows. So because I'm gonna keep the time ordering, ui. So first of all, this runs from the minus t sub minus to t sub plus. So the largest time is t sub plus because I'm gonna take that to be positive infinite, and then I can run that all the way down to the time where I have to hit the first operator, and that's going to be by I1. And then from that time, I can again start running to the time when I have to hit the second operator, and so on and so forth. And then eventually I will hit the last operator, and then I will have a last time evolution from that point to t minus. Okay, so I just literally stretched out. And this I can write it as, this is, that thing is, can be written as t plus 2, 0, 0 to t minus. You will see why this is useful in a minute, but I can write it as, because this is property of time evolution operator. You go from t minus to 0 at some point, it doesn't need to be 0. And then from that point to another point, right? You should be able to go there. Now let's clean this up. The numerator can be cleaned up. How? In order to do that, remember, the goal is to rewrite this expression in terms of Heisenberg picture operators. That means that you need to know how to write interaction picture operator in terms of Heisenberg picture operator. So I told you that thing already, but I'm sure you've forgotten that. So let me just tell you. Here is by H, it runs according to, with respect to Schrödinger, this, but then interaction picture with respect to Schrödinger picture runs according to H0. Which means that I can rewrite this thing as the 0 dagger. Oh, can you see from the back? Okay. How? It is a minus IHT interaction picture plus IHT U is 0, and that's it. So this is the relationship between Heisenberg and interaction picture. And let's see what this is. So this is nothing but time evolved according to the full Hamiltonian, and then go backward according to A0. That was exactly the definition of the use of I. Right? So this is use of I. Going from 0 to t. And this is Hermitian conjugate of that. Okay, so now I can use this relationship to rewrite this in a, so let me just write it in numerator first. Okay, so numerator looks like the vacuum equals to T1, and then what? I have to write that right. So that means UI T1 to 0. Now Heisenberg picture operator at time equal to 1, UI is 0 dagger, right? T1. So this is interaction picture operator. And then I have to write UI running from the T1 to the T2, and then I have to hit the second operator. Second operator, that's right, because T2 to 0, second Heisenberg operator, T2 0, dagger, and so on and so forth. You keep going until there. So now let's look at this. What is this? This is UI T plus 0. What is that thing? 0 to T2, T2 to T1, and then Hermitian conjugation says that T1 to 0. So it goes to 0 to 0. You see? Okay? So this entire chain collapses to 1. Okay? And then exact same thing happens all the way through. The numerator can be cleaned up as 0 vacuum to T plus 0. And then nicely, Heisenberg picture insertion. Then finally, you will have T minus. You should have this. Okay? This is just honest calculation, nothing mysterious. Good? So combining with that, then we almost have, therefore we get to the point where we have limit where t plus goes to infinity, t minus goes to minus infinity, that thing divided by Okay. Almost there. So almost looks like what we wanted to show, okay? Because we wanted to show time order product of that thing, but interacting vacuum divided by normal interacting vacuum. That was the goal. Okay, now I have to work out the remaining pieces. So let's do it. So let's first look at this mix. 0 minus, we are E minus goes to minus infinity. X on the back. So what I'm going to show is extremely useful and important fact. Okay, so you really want to know this. This will appear again in the later part of this question. Okay, so I'll finish up that part of the calculation and then I'll end the first part. The second part I think is very shorter. Okay, so let's look at this. Well, one thing that is useful is that let's actually look at this sandwich with some arbitrary state. It doesn't need to. It doesn't need to be specified at all. Okay, I just want to put something there. Then you see what this is. First of all, this is ut minus 0 dagger, and then u is full u compensated by 1 by h0, right? Again, I'm just using the definition. So that is u of 0 to minus, already I did the dagger of that thing, e to the minus I is 0. Okay, so if you use that definition, then what you get, so there's a limit, and then some random state, I don't need to know, and then full u, and then this is H0, and then when you act on that, the free vacuum, that's 0, right? That was the definition. So that, good. So far so good. Now, I'm gonna insert a complete set of bases here. By complete set, I mean really complete set of interacting QFT. Okay? So let's do that. So that will become limit t0 t minus goes to minus infinity, some random state. This is probe state. And then I'm gonna have, and what is this? So this is e to the plus I full Hamiltonian t minus, right? Now this is full Hamiltonian because it's a full time evolution operator. So if you go, this is schematically because in principle, since this doesn't commute, this can have a free part and interacting part. In general, this doesn't commute on different time. So when I write this notation, I really mean like there's time ordering with integration, all of that. But that's the simple presentation. So full Hamiltonian. Thank you. Okay. So this copy is away. So now almost ready to get pretty important result from here. Equal to. Now I said complete set. This include interacting vacuum. This include one particle state, two particle state, n particle state, and so on and so forth. So let me just split that into vacuum piece and the rest. The random state. Oh, let me just not stop. Interacting vacuum, but by definition of interacting vacuum, total Hamiltonian electron interacting vacuum to be 0, right? That was the definition. Let me say that again. H0, there's a vacuum. This is that. Full Hamiltonian vacuum is just interacting vacuum, as we defined. So that is that. And then plus the time limit again, 2.1. And then there's a sum over this, where this state is not equal to now interacting vacuum. And then there's a random state, and then state, vacuum and the E to the I energy of that state. Okay, I just wrote. So what am I doing? What am I doing? So I'm just going to sort it out this, but in order to do that, I split that object for left hand side one, or right hand side one, that object into full interacting vacuum component, and then the rest. The difference between these two is that full interacting vacuum state has a time independent overlap, and the rest has time dependent overlap. Okay. Now, when we take a lemma, now what we are going to do is the following. So I'm not going to, we can talk about it, but I'm not going to use Riemann-Lubeck lemma. If you like, you can use it. So now I'm going to take the limit. T minus goes to minus infinity, but I'm going to tilt just a little bit. Okay? So if you like, this little piece is e to the minus I. So there's a minus infinite direction, but I just rotate it a little bit downward. Yeah, so that's U1 rotation. Done. If you do that, then what happens is this. So let's look at this. That thing has a minus infinity. En. The reason why I picked minus sign is because first of all, this is oscillating this. This. And then what? There's a minus infinity little epsilon En. Okay? So there's an e to the oscillating piece e to the minus big number that I want. It doesn't matter how small the epsilon is. Okay. So long as I have a positive small epsilon, and then if I send the limit like that, all of a sudden the second piece just dies out. Okay? And then you're left with the first piece. So that's the math part. Let me explain the physics part of it. What does this actually mean physically? That means the following. You start out with a free vacuum. Now you want to reinterpret that free vacuum from the perspective of interacting Q at this state. Okay? So this can have overlap with all sorts of stuff. Right? It can have overlap with the interacting vacuum. It can have overlap with the actual other particle state in principle. Now, you just wait a very long time. Very long time means very large distance. Very large distance means a super low energy. So you prepare this state, and then go to the lowest possible state. Super long time. Just let system go. Reside. Okay? Eventually, it will settle down only on the state where you're left out only the interacting vacuum, and the rest is projected. Okay, this guy carries positive energy. Equals the energy in order to have this thing produced, right? Or you're taking the maximal possible, largest possible time limit. You go to the lowest possible state. Okay, so therefore the answer after this long calculation is the following. So if you take very long time limit, in this case minus infinity time, then I of this thing, meaning you're just gonna you're gonna do the time evolution acting on the free vacuum, and it will just end it up this. Basically interactive vacuum with the wave function or overlap. Okay, so it turns into that only. The rest is projected out. And then if you do the same thing, I'm almost done. If you do the same thing with that, now you go the other way, then you project out everything but interacting vacuum. So this thing is sometimes known as a vacuum saturation trick. Okay, just saturate the vacuum, nothing left over. Okay, we're almost ready. So let me just write with that help. This is that. That thing is equal to that. And then this thing is equal to that, and that thing becomes instead that. Right? Good. So now, hopefully now you can see by eye that this overlap part just drops out. And then we started out with this expression that we know how to do the Feynman diagram stuff. That is equal to time order expectation value in interacting vacuum divided by the norm of an interacting vacuum. Okay, and that was what? That was a coefficient of partial expansion of this J, Z of J. Okay, vacuum to vacuum transition in the presence of source. So just to summarize in two minutes, and then we'll be done. What is that? Okay. Now just realize that doesn't make any sense. Okay. Where are we? This.
Let's find me. So we are in line.
Why do we need that? Not. Does somebody live in the time zone, by the way? Maybe some of you. Nine. When did it? Oh, so one hour and a half or roughly. Okay, good. So let me summarize. What did I say? I want to study vacuum to vacuum transition amplitude in the presence of source. I defined Z of J, right? But in first I said if I do the this interaction picture business, but with actual interaction as a part of H0, but only the source term left out, right? Then it gives me Heisenberg picture again, right? And then I can expand it out as the power series as the powers of the J, and then what I get first is endpoint correlation function in Heisenberg picture. And then we can interpret that as Green's function, as a response of the system to the reaction, right? To the input. And then this is a completely new object, but I made a contact that is nothing but this, which is actual interaction picture with the same S matrix object, and we know how to compute the S matrices here. Or at least we know how to start the story about the S matrices. And then this calculation shows that that is actually equal to that. That was the thing that I was supposed to show. Okay. Now, what's left over is to learn how to extract from time order correlation function of Heisenberg picture endpoint function, how to extract the S matrix out of that. And that is LSZ reduction, which I will discuss after the break. Okay. Any question? All right. So let's take a break. How long?